So, let me find my my scribblings. We will begin. Today, I am hoping to, so I hope you guys have gotten the homework and a chance to look at it a little bit. You know, the first two problems are, they look like they're more than they are. I mean, I think Audric has worked some of them. He can testify to the fact that the bark is worse than the bite. Although I'm not sure. I mean, have you done the commutativity yet?
I didn't want to tackle it.
That looks tougher to me. I'm not sure how hard that actually is.
I was going to look at dumb, but to see if
I was.
the correction shows some proof of that.
I don't know.
I think it has an abstract.
All right.
Very loosely approved.
Let's see here. So I have, so I've shown you some of the big, like the sort of the big picture of the history of number theory. And I forgot to talk a little bit about the application. I mean, I talked a little bit about the applications in number theory. I mentioned that we'll study cryptography towards like right before test one, all right? This is, it's very funny that is something that we're studying because really, public key encryption is how most everything is secure on the internet, give or take a, technique. And that is very much number theory. And this is quite amusing because, back around the turn of the, going from the 1900s to the, 1800s to 1900s, there were, famous number theorists who were very proud of the fact that their number theory was completely esoteric, that it had no real world application, and that there would never be a real world application. They love this about it, So it is quite ironic.
Now, didn't they leave dimensional theory when string theory came around? Record said something about that too.
Oh, I don't know.
He said that like the dimensional theorists, how many dimensions you could possibly have, and looking for stuff, they left whenever the string theorists started looking at multi-dimensional space. They were like, oh, we don't want to use anything that has practical.
Oh, is that right? Huh. I don't know. But here's a quote. Leonard Dickinson, he apparently lived 1874 to 1954, so somewhere in there. He said, quote unquote, "Thank God that number theory is unsullied by any application." So this is great. I think it's a pretty hilarious quote, because another thing I should have told you last time is that one of the principal places where number theory is taught is actually to computer scientists. Really, discrete mathematics is elementary number theory. It's the study of different base systems and things like that. It really is part and parcel of number theory. Oh, really? Oh no. But you chose a wise path. Let's see here. All right. So I thought that was fun. The other fun thing is one of the stories I was going to tell you guys last time is so nowadays we tend to call it number theory, and as I told you, there's algebraic number theory and there's analytic number theory, and there's a fruitful interplay between those two things. But classically, back early 20th century, it was often called higher arithmetic. All right, and so classically, you might call number theory the study of arithmetic, and so you can see how this can lead to kind of funny events. There's a rather famous book by Sayre called A Course in Arithmetic. All right. And so a very high-powered number theorist, they happen to live in New York. I don't know which, maybe Columbia. I'm not sure really. I couldn't find the name of it. My brother told me this story, and I've tried to find it online. I haven't been able to source the name. I know it's a true story, and I know it's in a New York Times article, but I am unwilling to give them my personal information so I can get behind the paywall. So anyway, long story short, there's this guy, he's riding the subway train, he's reading Sayre's A Course in Arithmetic, right? And of course, you can imagine what happened. Elderly lady praised him for his courage to return to school studies so late in life. So it's even funnier if you understand how deep and like groundbreaking that book by Sayre was. I mean, it was one of the more difficult math books that's ever been written. But to this lady on the train, it looks like he's a grown man studying arithmetic, which I don't know. I found it was funny. Those are the jokes that you wanted to be spared from. So it wasn't too bad, was it? I mean, it could have been worse. No?
I think the note Benjamin.
My Benjamin?
Yeah.
What note did he leave you?
Benjamin was his son, and when we were doing research, I met him quite a bit. He left me a pass to Ninjago City.
You have a pass to Ninjago City. That's awesome. All right. Okay, so let's see here. So let us talk about the division algorithm. So my goal for today is to talk about the integers, the concept of like greatest common divisor, and Euclidean, the Euclid algorithm, also called the division algorithm, and of course some of the theorems we know about primes. Okay, that's the goal for today. So just to give you a preliminary sort of calculation. So suppose you want to think about 11/3, right? So we think about 11 minus 3 is 8, right? And then 8 minus 3 is what? 5, right? And then 5 minus 3 is 2. And then at that point, you can't subtract more, right? You're kind of stuck there. And so if you put these things together, you can see that what you have is 11 is equal to 3 times 3 plus 2, right? Or you could also say 11/3 is what? 3 plus 2/3, right? So in number theory and also group theory and so forth, we more often than not are more interested in this way of looking at things than that way of looking at things. All right? And so the division algorithm has to do with finding that kind of correspondence. All right, so here's the theorem. If A and B are integers and B is greater than 0, then there exists a unique quotient Q in Z and remainder R in Z, for which A is equal to B, QB plus R, and 0 is less than or equal to R is less than B. So this is the division algorithm. This one form of it. So how do you prove this? All right. So the proof is by the well-ordering principle. And what you want to do is you want to construct a set. All right. And here it is. So we'll let R equal to A minus NB, such that N Stupid typo in my notes. All right. So I'm assuming that A and B are integers, that B is positive, and let's see here, such that how can I say this? A minus NB is greater than 0? Do I want it equal? I'm sorry, there's a typo in my notes, which has messed up my thinking. Yeah. Okay, well, let's just go with this, all right? So to apply the well-ordering principle, what do we need? We need that this is a subset of the natural numbers, right? And if it is, then it has to have a least element. That's the well-ordering principle, right? So I guess I need to say what n is, right? That's what's bothering me. N is an element of, I suppose, Z. It's really just the idea of the example I erased, right? You start with the number, and then you subtract off copies of the dividing number, right, until you get basically as small as you want. And so the idea is that the smallest number in this set should be the remainder, right? So can you, okay, so certainly this is a subset of, this definitely is a subset of the natural numbers, because we're looking at what, a minus nb, so the product of natural numbers and subtract a natural number from another. I mean, this is definitely again, an integer, and this makes it positive or not negative. So this is definitely a subset of, I'll call it n sub 0. So for purposes of not writing this 1,000 times, I'm inventing n sub 0 to be Rakovich's natural numbers. Half of the civilized world includes 0 in the natural numbers, and then the rest of the uncivilized world, like me, starts at 1, typically. Anyway, so it's definitely a subset, right? Is it non-empty? Can you convince me R is non-empty? Why is 0 in R, though? How do you get to 0?
Because it's greater than or equal to. Is that what you're thinking? Yeah, but sounds like all sets contain themselves, but they also contain the empty set. Or no, I guess it's superset. I'm thinking of something else.
Okay, so how about this? If A is greater than 0, right? Then set n equals to 0 to C. A is an element of R, right? So R is non-empty, right? So I agree with you. We can put n equals to 0 if A is non-negative, right? What if A is, but we don't get to assume A is non-negative. So we have to consider cases, right? What about if A is less than 0?
A is less than 0.
I say
Set n equal to
-1. But how do you know that
a plus b.
a plus b is non-negative? You don't know that.
Say a was in.
We're not. All we know about a is it's an integer. B is what we're assuming is positive. How about this? What if we put n equal to like a? Would that work? Then what do you have? You have a minus a times b, right?
Where a b is greater than 0.
So that's equal to a times 1 minus b, right?
Yeah.
Now, a is negative by assumption. And what about 1 minus b? Remember, b is assumed to be positive.
Then it'd be negative.
So that means that this is negative. The product of negative things is positive. So this is greater than 0. Consequently, a minus ab is an element of R, right? Which then is non-empty. Okay, so that's everything, right? Either a is greater than or equal to 0, or a is less than 0. We've covered all our bases. R is definitely a non-empty set. Therefore, we may apply the well-ordering principle to this non-empty subset of the natural numbers, including 0. And so let R be the smallest element in R by the WAP. Now what do we need?
That it has a start. Oh wait, yeah. Well, in principle says it has to have a first entry. Because we can say it's a subset of the natural numbers.
So yeah, R is equal to, what is it? A minus NB for some n, right? Because it's in there. And so what is that? What is that? I mean, we can rewrite this. What's this give us? A is equal to NB plus R, right? So apparently we should make n be the quotient, right? That would be half of what we need. There's a remainder for which a is equal to qb plus r. So if I just set q equal to n, we got that. But it remains to show that the remainder is between 0 and b, right? All right. So how do we show that the remainder is between 0 and b? I think contradiction proof is the easiest thing here. So suppose otherwise. Suppose that the remainder is, let's see here. Suppose the remainder is greater than b. Right, that would be, we know that the remainder is positive, right? So we don't have to worry about the case that, like negative, like all we have to worry about is it could be greater than, or I guess greater than or equal to b I should worry about, right? Why would that give us a contradiction?
Because if it's greater than b, you can divide them one more time.
Yeah, I think so. But in terms of this set, why does that contradict R being the smallest element? That's what we have to contradict here. If we're assuming, why does this, how can we find a contradiction from this? R is assumed to be the smallest element, right?
Yes, sir.
So suppose r is greater than or equal to b. Why would that contradict?
A minus MB and R can't be greater than R.
A minus. Oh, you say it's from here?
Yeah.
A minus nr?
Yeah. So B has to be equal to R, right?
And I didn't say that.
Greater than, or B has to be less than or equal to.
This is towards a contradiction, right?
Yeah. Yeah, I mean,
I think you have the right idea. Let me just like try to write it out. So Notice that what I have in the notes here is that r prime is equal to a minus n plus 1. B is greater than or equal to 0. Does that make sense? See, I think I'm starting with this star, right? And I'm subtracting. So this says, this right here, right? It tells me that r minus b is greater than or equal to 0, right? So that means that a minus nb minus b is greater than or equal to 0. So I can call, and that's a minus n plus 1 times b. I'm calling that whole thing r prime. If that's greater than or equal to 0, that means, like you said, you could subtract again. R prime is an element of R, right? But what else is true about R prime? Is R prime, is it smaller than the smallest element?
yeah.
It is, right? Yeah. And which is a contradiction, right? So therefore, R is indeed the remainder, in the sense that it has to have 0 less than R less than 0 less than or equal to R less than B. Because to suppose otherwise gives us a contradiction. Now, it remains to show that it's unique, but I think I'm going to skip over that in the the interest of moving along here. I will post these notes that I'm working out of. I have some pages of LaTeX I've written up. So once I find it, I'll post it for you guys. But I'm trying to work it through here rather than just copying it down, All right. So I say we can actually say more about Q and R in the case B is greater than 0. So in fact, A over B is equal to Q plus R over B. And what is Q? Where it's actually equal to the floor function of A over B. All right. So some examples of the floor function, just so you see how it works. The floor of minus 0.4 is minus 1. The floor of pi is 3. The floor of n plus any little epsilon is n. All right. So if you have a calculator, right? If you have a calculator, you can kind of put the division algorithm for a positive, dividing number into practice by just using the floor function and some like common sense arithmetic, calculator arithmetic. So just to sort of demystify it here. So if I take like 324 over 11, that's equal to 29.4545 repeated. All right, so the floor of 324 over 11 is 29, right? And so what I extract from all that is 324 over 11. Well, that's equal to 29 plus 0.454545, repeating, right? In other words, 29 is the, the integer part of this improper fraction, right? And if you multiply that by 11, we get the outcome of the division algorithm, right? So multiply this by 11, you get 324 is 29 times 11. And 11 times 0.45 actually works out to like 4.9995, which you can kind of like tilt your head and squint and go, aha, it's a 5, right? Now, what if, it actually doesn't matter, right? To figure out what this number is, once you figured out that's 29, you can just take 324 minus 29 times 11, and you'll get 5, right? So you don't actually have to monkey around with this repeating decimal thing to find the 5. You can find it by subtracting off the multiple of Q from A. So this is, I'm kind of just telling you how we can implement the division algorithm using a calculator is all.
Okay. So would you always use 11?
11, oh, this is just an example. You could have division by something else,
Which is because 11.
Yeah, this is, because 11 was there. Another example, let's see here. I had 456. And so this is not fitting into the, not fitting into the division algorithm as stated. But if I have 456 divided by minus 10, well, that's minus 45.6, right? Which I could write as minus 45 minus 0.6, right? And so if you take that, tilt your head and squint, you can see what you got is 456 is equal to minus 45 times minus 10 plus 6. All right. So this calculation I did is just a cautionary tale on how the division algorithm plays out with a negative dividing number, right? So here, B, quote unquote, right, is negative 10. It's less than 0. And what happened here? What is this minus 45? So if we look at 456 over minus 10, what is 45? Of course, this is minus 45.6. What is minus 45 to this? It's not the floor, right? The floor of minus 45.6 would be minus 46. Minus 45 is what's called the ceiling. So the ceiling of 456 over minus 10 is minus 45. So this comment I made up here is for positive divisor. If you have a, and I say divisor, but I really mean to say dividing number. If I divide by a negative number, I use the ceiling function to find the quotient. All right? But of course, if you look at the argument that we just made for positive dividing number, it's clear it's just a matter of bookkeeping that we can make the same kind of argument for B being negative. And I have an explicit proof in the notes where I just basically steal it from the positive theorem. So I'll let you look at that. In fact, I will modify the theorem. Here's what we actually have in general. The non-zero division algorithm for A and B integers and B not equal to 0. I'll make the modifications in red. There is a unique quotient Q and remainder R for which A is QB plus R and 0 less than R less than, instead of B, How do you fix b when b could be negative?
How do you fix B?
How do you fix this statement so it's still true when it's...
When B is negative?
Yeah, you do this. Plus or minus. So you put absolute value there and it fixes it. Because that's what we did over here, right? So like, if you look at the silly example, minus 10, right? So notice the remainder here was 6, right? So you have like 0 less than 6 less than the absolute value of b, which was minus 10, right? So anyway, okay. All right, so I have now spent entirely too much time on this topic. And yet not enough, because actually this is not the part we're interested in. Well, that's not quite honest. We are interested in this, but what we're more interested in is the Euclidean algorithm. All right, so far I've just told you the division algorithm. Actually, I haven't told you the division algorithm.
Yeah, you did.
I did?
PB plus R.
And yet that's not, I have juxtaposed two words in my mind.
Oh, QB.
What is that thing called then? Oh, okay, so the Euclidean algorithm is what I'm thinking of. All right, Euclid's algorithm. All right, now before we get to Euclid's algorithm, I owe you some theorems and some definitions. All right, so I think I'll start over there because I've got a lot ready to do. So definition, A and B integers, all right. We say B divides A. That's not a fraction, that's a statement, all right. If there exists C in the integers such that A is equal to BC. All right. If B divides A, we also say B is a factor of A, and A is a multiple of B. I think those are well in line with your current understanding of the words factor and multiple, right? I'm not really doing anything novel there. Definition. If P is a natural number such that n divides P implies n equals to P or n equals to 1, then we say P is prime. This definition is almost correct.
If B divides A, we also say that what is a factor?
If B is a factor of A. Yeah, oh, that's a B. Yeah, sorry about that. Now, my definition...
I learned you're right.
Oh.
That is a skill in its own, not be just in math general. Math teacher, right? Yes.
So what's missing? I mean, basically, here's the question. Is 1 prime? The answer is no. 1 is not prime.
But it's only factored for 1 itself.
I know, but we don't say 1 is prime. Because when we're talking about prime factorizations, you don't want to allow 1 to be one of those things. It's not. Well, I'm relatively sure 1 is not supposed to be a prime. Now you've made me doubt myself. I'll look into it some more, but I'm pretty sure we shouldn't say 1 is a prime. Tell you what, this may be one of those things where the abstract algebraists say, no, 1 is not a prime because we have an abstract definition of prime, and letting 1 be prime throws that into chaos. Whereas all of the elementary number theorist people are like, yes, 1 is a prime because otherwise we have to say more than the sentence. We like to just say the sentence. So I don't know. So I guess it's under review in this course at the moment then. How about that? But I think 1's not a prime. All right. Proposition. A couple of these are homework problems, actually. So let A, B, C, D, M be integers. Then 1, if A divides B and B divides C, then A divides C. 2, if A divides B and C divides D, then AC divides BD. 3, if M is not equal to 0, then MA divides MB if and only if A divides B. And, oh man, my numbering is all in the wrong font or number system. I meant Roman 1, Roman 2, little Roman 3, and IV 4. If D divides A and A is not equal to 0, then the magnitude of D, the absolute value of it, is less than or equal to the absolute value of A. Footnote, I should mention, I am partly following the excellent presentation of Jones and Jones elementary number theory, which I almost used as the text once. In fact, I looked at the syllabus for this course. I think Dr. Rogers has used Jones and Jones as the book last time, so it's kind of funny. It's a good solid little book. It's not quite as much fun as Stillwell. But. All right, so how do we prove these things? Let's prove one of them in here. 3 and 4 are your homework, so you'll prove those. Let's see here. So, which one do you guys want me to do? 2 or 1 or 2?
They look pretty similar.
Okay, thank you. Audric is the decider. I like it. So suppose A divides B and B divides C, right? Then there exist M and N in the integers such that what? B is equal to NA and C is equal to MB, right? By the definition of divides by, right? B has to be a multiple of A, C has to be a multiple of B. I just think in multiples. I get it, I admit it. I think in multiples. This divides by business drives me nuts. Maybe that might be evidence I'm not a number theorist right there. But anyway, so great. So we're trying to prove A divides C, right? So we'd like to see that C is a multiple of A. If we can do that, we've showed A divides C, right? So consider MC is equal to MB is equal to what? M na, right? Because I'm just taking this and plugging it in there, right? But what can you say about m times n? M times n is an integer. Thus, A divides C, and we're done. Okay? Now, this brings us to theorem, and I think the proof of the other one's pretty similar. Theorem 3.4, we have A1, A2, AK, and C in the integers. All right, then 1, if C divides A sub I for I equals to 1, 2, all the way out to K, all right, then C divides U1 A1 plus U2 A2 plus UK AK for all U1 U2 UK in Z. So what this is saying is that if C divides each one of the A sub i's, then it will divide any integer linear combination of the A sub i's. So divisibility plays nice with integer linear combinations. This is, I'm actually not going to, I have a proof of this in the notes. I'm actually just going to prove it for two things because I think that proof is easier to follow. But I'll state two before I prove one. Two is A divides B and B divides A if and only if, guess what? A is equal to plus or minus B. All right. So here's the, I state this as corollary. 3.5, it's actually just a special case of number 1, which is that if C divides X and C divides Y, then C divides AX plus BY for all A and B in the integers. So let me prove the corollary rather than proving number 1. The proof is just as difficult, just less clumsy. All these proofs are kind of the same, give or take a argument about. Sometimes, like the one about M, you might need to know something about, like, you can't factor 1 in the integers, right? Like if you get a product of two integers equal to 1, it forces the integers to either be 1 and 1 or minus 1 and minus 1. That's kind of like a fundamental thing you can claim to know in here. Or you could prove it using the model constructions that I gave you in problems 1 and 2, if you're so inclined. Okay, so let's prove this. Here we go. Proof. So C divides X and C divides Y implies that there exists M and N integers such that what? X is equal to MC and Y is equal to NC, right? M as in mommy, N as in nanu nanu. It's a Morkin Mindy joke. Definitely before your guys' time. Before my time as well. Anyway, so then in order to show that C divides AX plus BY, what do we need to know? We need to show that C is a multiple, that AX plus BY is a multiple of C, right? So let A and B be integers. We have to do it for arbitrary A and B, right? And consider AX plus BY, right? And all we're going to do is we're just going to plug in the data that we already know. X is equal to MC, Y is equal to NC. Plug it in, what happens? AMC, I wouldn't buy stock in them right now, plus BNC, and factor out, you got yourself an AM plus BN times C. And since AM plus BN is an integer, we find C divides AX plus BY, and that suffices to prove the corollary.
This is, when you abbreviate that a bit, it's like corresponding to 3.5.
Corollary 3.5, yeah.
Oh yeah, corollary 3.5. This brings me to a definition, which of course is quite important for this course, but I think you've known it since, like, I don't know, second grade, third grade maybe. Definition: if D divides A and D divides B, then D is a common divisor of A and B, right? Now, let's think about this. Number 4 of the proposition, one of the things you're going to prove, says that the magnitude of the divisor is at most A. Right? If D divides A, the magnitude of D is at most A. So, if you have a common divisor, right? If D is a common divisor of A and B, it's at most A, right?
Well, yeah, they're integers, so if it's over 8, you get a not, you get something not in the integers.
Yeah, so it's at most A, and it's also at most B, right? So if you look at this, D can be at most the maximum, actually the maximum, maybe the minimum of A and B, right? Anyway, the point is, D can't be bigger than, like, certainly bigger than A times B, magnitude of A times B. But if we assume D is, we can assume D is positive, right? And so if you think about a positive divisor, it has to be between basically what? Between, if it's a positive common divisor of A and B, it has to be between 1 and the maximum of the absolute value of A and B. But this is like a finite list of numbers, right? So if you think about the set of all possible divisors, there has to be like a greatest one. The smallest one is going to be 1, right? 1 is a divisor to any number. So we always have common divisor of 1. But the greatest common divisor is of more interest, right? And you can see that that has to exist if you just think about property 4, right? So that the greatest common divisor, GCD of AB, is the greatest common divisor of A and B, right? Now, how did you find the greatest common divisor when you were, like, in elementary school? Do you remember how you did it? Like the example in my notes I have, find the greatest common divisor of 105 and 90. You're like, I just kind of look at it and...
Yeah, the book
So if you want an algorithm, right? Which
15, I think it's 15.
so if you want an algorithm, what you can do, right, is you can say 100. So basically, find the prime factorization of it, right? So 105 is 3 times 35,
15.
which is 3 times 35, which is 3 times 5 times 7, right? That's 105. And 90 is 9 times 10, right? Which is 3 times 3 times 2 times 5. So there you go. Those are the prime factorizations of 105 and 90. So to find the greatest common divisor, you just select pairs of prime divisors as much as is possible, right? Like you can pair a 3, and we can pair a 5. Of course, the other 3, the 2, and the 7, there's no way to get both of them together in both. But like you said, 15, because 3 times 5 is 15. So, yeah. Very good. Now, it's very good, right? But it's also very bad because, like, that is definitely not the way you want to, find the greatest common divisor of, like, a large number and another large number, right? Because finding prime factorizations of integers is actually kind of a pain. So how do you do this? All right. Let's see if I can. Oh. I'm really hoping I have this thing posted on my website. Otherwise, I have to email it to myself, which is going to, like, eat a bunch of time. Well, I mean, not a bunch of time, but just, hopefully I have it here. Man, this day is long for me, you guys. I am worn out by the time I get to your class. This is not a good thing.
Imagine having 3 hours to go straight, which was the original plan.
3 hours straight? Yeah, no.
See, everyone's complaining about Rakovich's class, and me and the students that were in your, me in differential geometry and whoever was in, what class did you have Mondays with Carson?
Oh,
Technology or something?
yeah, whatever that
We're
is.
all just like, you don't know. You don't know the long classes.
Oh, the 4-hour,
Yeah, 3 hours.
4-hour differential geometry?
Yeah, I was
Ay,
like,
ay, ay.
You guys don't know the long classes.
I just,
8 o'clock, nothing. What? It's essentially the geometry of curved surfaces. So you know how, like, we typically do geometry on flat planes.
oh, good, I
How
found
does
it.
it change? How does geometry? How do things change over a curved surface? Straight lines are no longer straight lines, and you have to take note of different.
I hope you guys don't mind. I'm going to use the projector a bit here because I've got a fair amount of material to cover before time's up, and I don't want to end up going 10 minutes over or something stupid. And I will provide, like, so I do think some of these proofs that I'm about to, like, talk you through, they're totally accessible to you. So, they might make a good test question. I tend to forewarn that kind of thing. Like, when we get closer to the test, I'll be like, I think the proof of this, and this make good test questions. That's something I'll do. Yeah. Now, pretty much, if I state a definition in here, you need to know it. Like, it's like, that's just, I think that's just kind of advanced math class 101, that's just true. Let's see if I can move it over here if it helps, maybe. You're fine, it's up above you. Well, anyway, you guys are here, so. Now, this is already posted on my website. If you, let's see here. Well, I'll send you guys a link later, but just, I'll show you right now. So on the number theory site, it's like this modular arithmetic supplement to add depth and treatment of modular arithmetic. That actually starts with integers, which is what we're doing right now. So here it is. So I just went through Theorem 2.1, of course, which is the division algorithm. There's the proof of uniqueness I skipped. My resident Chinese scholar tells me that Chinese a over b has the dividing number b and the divided number a. I've been trying not to call b the divisor, because when you say something's a divisor, it implies that the remainder is 0, which we don't know. Anyway, so there's the proof of the non-zero one that I skipped. All right. Here's that proposition we just did. Actually, I have the proof of 1 and 2 in the notes. Oh no! Avert your eyes!
I like how you highlight it.
That, I think I have solved one of your homework problems. Oops. Yeah, there's the proof of that one. But anyway. All right. So here's the lemma. So I'll stop scrolling here eventually. I wish I could get rid of this stupid. Can you make it? All right, well.
You can get rid of it. I don't know exactly how.
Yeah, I was fighting with this the other day, and no, it's still there. Not helpful. Present doesn't help. That's a road to nowhere. I think this is good enough, isn't it?
Yeah.
All right. So anyway, here it is. If a, b, q, and r are integers, if a is equal to qb plus r, then the greatest common divisor of a and b is the same as the greatest common divisor of b and r. So that's kind of interesting, right? So to see why that's true, let's see here. Suppose we have a common divisor of, if we have a common divisor of b and r, right? Then qb plus r is an integer linear combination of b and r.
Yeah.
Therefore, a also has that as a divisor. That divisor we're talking about. On the flip side of things, if b and r have a common divisor, excuse me, if a and b have a common divisor, then a minus qb is equal to r. So that means that